Ready for the Friday Colloquium. So today we have Professor Laenen from NICHEP. A brief biological sketch of our speaker today. Professor Laenen did his PhD from Stony Brook with Jack Smith, and then he was a postdoctoral fellow at CERN and Fermilab. Then he became a professor at Utrecht University and also now at University of Amsterdam, Institute of Physics actually. He's also the director of NICHEP and director of Institute of Physics and also NICHEP, right?
Not NICHEP.
Nothing, okay. And more importantly, he's also the vice president of CERN Council, and he's also on the finance committee of the CERN. So he's a very important guy. So okay, today he's going to talk about stress testing the standard model of particle physics. Over to you.
Thank you very much, Sudhir, and thank you for coming. It's a great pleasure to be here at ISC again. I've been coming here over the years quite a few times, and it's been very nice these past 2 weeks, and I intend to also come back in the next years. What I'll be talking about today is stress testing the standard model of particle physics, and particularly I want to talk about what I mean with this, what I'm stress testing this model, why you would want to do this, and how. A little bit of impressions of each of those questions, of the answers to those questions, such that hopefully when you leave here you have a sense of what this enterprise is about and what it can yield us. So it will not be linear, so we'll have elements, some a bit more technical, some a bit more outreach level. Hopefully there will be something in it for all of you, or you may all leave dissatisfied because there was nothing in it for you, but we'll see at the end. Now, I do want to begin with commemorating our colleague and also my friend, Professor Rohini Godbole. Passing is a tremendous loss for the Institute. For particle physics in India and really well beyond. Rohini and I had the same advisor in Stony Brook, Jack Smith, and she was a few years ahead of me, so I didn't meet her there. I got to know her later. For extended visits also, she came to the Netherlands in 6 months in 2011 to Utrecht, where she taught the Beyond the Standard Model class. And really there was a set of 20 students very devoted to the class and to her. And later she visited the University of Amsterdam as a Van der Waals chair, again inspiring students and colleagues at NICHEP on issues of physics, but also of the importance of paying attention to the role of women in science. And not just NICHEP and the University of Amsterdam, in fact throughout the Netherlands she was helpful and known and a friend to all, and she was on many advisory boards, evaluations for Dutch institutes and helped Dutch physics in many ways, and for that I think Dutch physics will always be grateful. So I have a few pictures that I'd like to show from over the years. So this is of course clearly Amsterdam, very recognizable. This is with her successor at the University of Mumbai, in a sense, Professor Anuradha Mishra, and a student and in front of NICHEP. Here is with other fellow student of Jack Smith, Jos Vermazeren, who will come back in the talk later. And this is Bert Schellekens, known to some of you. And here is a picture in Utrecht. And she really wanted to go here because this was the Caroline Bleecker building. And she taught me something there also. The Caroline Bleecker was the first female entrepreneur, science entrepreneur in the Netherlands in the 1930s, which is really going against all trends and culture at the time. So she really was very impressive, and Rohini was very keen on learning more about her and see what happened there. So I think this gives you a bit of a vignette, and I think I'll miss her, and I'm sure we all will miss her very much. So now, turning to the topic of the colloquium, let me first have a little movie, just for those who haven't seen this yet. How does the Large Hadron Collider with CERN work? Well, here you see protons being accelerated in various injector accelerators, smaller accelerators to get up to speed, and then finally in the big Large Hadron Collider ring, and only one detector, unfortunately not the one from you, the CMS detector, but the Atlas detector is drawn here. And they brought into collision in the middle of the detector, And all that energy, E, is converted to lots of particles via E is mc squared and the laws of the standard model. And then you essentially have this enormous detector taking a digital picture of all the tracks coming out and seeing what particles are they and did something happen, interestingly, here. Most of the time not, but a few cases that something interesting happened, you have an excellent detector and all the software around it to distill that. So that's how collisions at the LHC happen. Now, what is measured in these collisions? Well, detectors are segmented and layered, and each has specific capacities for specific types of particles, trackers, calorimeters, and they measure how many particles, which type, etc., fly in a certain segment per collision. And this can be translated in so-called a differential cross-section. So what is the probability of finding certain particles in certain regions? And this differential cross-section, this measurable quantity, reflects fairly directly the strength and the structure of the interactions that cause that pattern. So in other words, the interactions among the particles. Now, this can also be calculated and using standard model calculation rules, and you compare and you draw your conclusions. That's the business of comparing data with theory. So the theory in this case is the standard model, also known as the theory of almost everything. Almost, of course, is rather serious. Gravity is not in there, and other new forces. This is the picture of the particles. You know it very well. The quarks, the force particles here, Z, W, gamma, and gluon, and here the leptons, including the 3 neutrinos in the middle here. A bit spooky, the Higgs boson. All of them have now been seen. So elementary matter, these are the fermions. They can be grouped like this. This is stuff that we're made of, the electron up and down quark, and out of those you can make the proton and neutron, which make up the nuclei and the atoms of which we're made. And then we have these electron neutrinos, which are very hard to detect. They fly easily through your body, 10 to the 15 per second through all of you. Come from the sun almost exclusively. And this makes up so-called first family or the first generation. Turns out that nature has made 2 more copies of this with similar particles and just heavier masses and different names. Right? The heaviest here is the 3rd generation with top and the bottom quark. And for all these fermions are also the antiparticles. They have all the quantum numbers opposite, not the mass, but the charges and all that. So that's elementary matter. And then there is also force in the standard model. Particle exchanges is one of these outreachy slides, but I always liked it. Unfortunately, I never could find a movie for it. But the picture says it all. Force is in the theory is particle exchange. You have your 2 people on roller skates throwing a pretty heavy ball back and forth. And you can sort of see you can imagine what happens. They start drifting apart. They exert a force on each other without direct contact, but just by exchanging a particle. That's a pretty nice analogy of what happens quantum mechanically as well. So what are these force particles? Well, here they are, and I've listed the force that they correspond to, the name of the particle, the typical strength, and the phenomena. So electromagnetism, photon, you know that very well. Typical strength is 1/137. It's not an integer, 0.01, I think. And this is, well, all the stuff we know, atoms, chemistry, light, mobile phones, etc. The weak nuclear force is transmitted by exchanges of W and Z bosons, and this is the typical strength, a bit stronger than this, and drives the processes at the sun, but also radioactive decay. And also very important, but more shielded, is the strong nuclear force mediated by gluons. They hold the quarks and gluons inside the protons together and hold the protons and neutrons together in the nucleus, but otherwise fairly short range. And then there is the force of gravity. There might be gravitons, we don't know. But you also see why we left it out. At the level of elementary particles, the strength is 10 to the minus 41 compared to these. So you really need first to have a huge particle like a planet to make it actually felt. So that was the standard model in a very picturesque way. And in a bit more detail, it looks like this. Now for you, this actually may make some sense. Right? You see here the Higgs potential, this is the Yukawa interactions, this is the kinetic term for the fermions. This is the gauge field interactions, etc. If you really want to work it out in more detail, it looks like this, which is a bit more correct. It's not particularly pretty. But what it does show you is all these terms. This is the Lagrangian of the standard model that defines what the model is. All these terms represent some kind of either propagating particle or a particular interaction. There's a lot of structure here, a lot of stuff to test to see that is it really like this, or are there deviations. So that's a serious business to do. This shows at least the complexity. Now, a few slides on what is behind this Lagrangian and how you should think about this quantum mechanically. So the Lagrangian is phrased not in terms of particles with their coordinates and their velocities like you would in classical mechanics. It looks a lot like it. You know, classical dynamics can be derived from the Euler-Lagrange equation like this. Right? I hope some of you've had this in early classes. But you actually, instead of coordinates, you would place them by quantum fields. Now, we have to go up a few levels. So here we have what you know. From this, for example, leads you to Newton's laws. This is a Lagrangian, and this equation of motion follows in turn from a variational principle. So if you say this is the action, the interval over time of this thing, and you vary it to make it extremal, then that leads to this equation. Then you can go up one level and say, okay, why would you impose this? Well, there's something called the path integral, which is the integral over these paths. And if you have a stationary phase, that's when you don't have all these phase cancellation, but when the variation of this is zero, in other words that's when you get the contribution to this integral. So we got more and more abstract every time the reason for the next equation, but that's what the path integral is. So a bit more about this path integral. Here it is, the integral over paths, the sum over paths, with this phase factor in front. You see h bar here. And this is a picture. Suppose you have a system, not specified, that has to go from configuration A to configuration B. And these are all the possible paths it can take, from the smooth ones to the crazy ones. They're all in the integral. So each path is weighted by such a phase factor, by the action corresponding to this path. And what is now the dominant path is for that for which S changes least, the stationary phase. Otherwise it all extinguishes because of the phase. So instead of such a path from a particle that travels, you now take a field, electron field, a quark field, etc. And they don't depend on time, but on space-time. And particles in this picture are field pulses. As you can think of a sheet, and you have a bump in there that travels. That's the particle in field language. So you again do a sum over paths over all these field configurations, and that's really what makes it quantum. I admit it sounds very abstract and a bit magical, but it actually works very well and very precisely. So once you have such a path integral, that's your definition of the quantum field theory, and then you can start doing calculations with it, either directly, like in lattice gauge theory, or through Feynman diagrams by expanding it, and that's what we'll turn to now. So this was a bit on the path integral. So, based on such a quantum field theory of the standard model, what you do typically is you think about collisions, and you think of theoretical versions of collisions, and you do that through Feynman diagrams. And they lead you to a perturbative approach. You can compute quantities a bit better and better and better as you compute more diagrams. We'll come back to that. And the perturbation theory is done in terms of expansion parameters, and for that we use the couplings of the interaction strengths. And this is really an excellent method of systematically improving predictions, and this is Feynman, for those who don't know. So these Feynman diagrams, it's worthwhile spending some time because they're just marvelous. Towards the end of the 1940s, theorists, in order to do calculations with long, very, 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 very long formulas, turn the pages around, use all kinds of people to write long formulas. And then he came along with a fantastic shorthand notation, which is this diagrams. So here's a diagram showing electron scattering through photon exchange. So here's the exchange photon. We have two electrons coming in, exchanging a photon. We We talked about this. And then they fly apart at a different angle. That's the scattering. So the elements are vertices and flying particles. So you build such a diagram up from free flight and interaction. So we need 4 times the propagator for an electron, once one for flying photon, and 2 interaction vertices. This is very much like, you have IKEA here, the Swedish furniture store. This is very much the IKEA tool, if you particular students know this, and me too. And with that, screw it together when you get such a diagram. In fact, the genius is that for each bit of graph, you associate a bit of formula. And what you do when you put the graph together, you also put the bits of formula together, and this actually can lead to a prediction. So it's a straight and very determinative algorithm to go from the diagram to a formula, and thereby a prediction. That's really how nicely Feynman diagrams work. Okay. The thing we want to do is think about precision stress testing. Really make sure that we get the most out of the data and test the theory most. So the concepts that are often talked about are the concepts like precision, like accuracy, error, and uncertainty. And it's maybe good to go over those concepts a little bit to difference. Now, here is our perturbative approach to observable O. We do calculations, and they lead us, and the expansion parameter is alpha, the small number, and your calculation leads coefficient Cn, and you do it up to order m, and this, in the end, there will be some uncertainty stuff you haven't computed that is called delta O. So precision is then to compute to order m large enough such that this is small enough for your purposes. So you say, I want a 1% error, then I need to calculate to 2nd or 3rd order, or maybe 100th order, depending. So that's precise. But it can be a small variation on an incorrect result. Right? So it's a very precise, but maybe not accurate. So that's important to keep that difference. Now, and the error is a measure of accuracy. How good are you actually to the true value? And the uncertainty indicates a range that you have in which the true value could lie. And accuracy can be both, theoretical, but particularly also experimental. You have systematical and statistical errors. Now, when you, of course, confront theory with measurement, the smaller you can get delta O, the more meaningful the comparison will be. On both sides, theory and experiment. But if you have smaller O on both sides, if you have small on one side and huge on the other, you can't do much. Both need to be good. Both uncertainties need to be small. So that's really what we should be doing. This is a highly sophisticated instance of what we call the scientific method. That's how we learn. So to give you an example of precision versus accuracy, I always like this plot. It's pretty old by now, but it's from the CDF experiment. The rapidity distribution of so-called Z bosons in perturbation theory. And the rapidity is big Y, it's on the Y-axis, on the X-axis. And here is the differential cross-section that we talked about. And here are the data points. You see them. Now, if you would do the simplest level calculation, the leading order, then you will get this. And you see this is the uncertainty band. It's very, very precise, but not accurate. And people then did corrections, the next to leading order, then you get this band. Also precise, but not accurate. And only when the second order, the next to leading order was calculated, then you start reproducing the data. So this is it's a lesson about difference of precision and accuracy, but it also is a lesson that don't claim victory too soon. Right? It might be that what you're measuring is just higher order corrections. So what is the status of precise standard model theory versus data now? Well, as you know, a standard model works marvelously well, often at the 1% accuracy or better. But we think it cannot be the final answer of the microcosmos. It does not answer some questions, some issues that we know are there, like dark matter. What is the nature of dark matter? There's no candidate in the standard model. Where did all the antimatter go? In standard model, we make always almost equal amounts of matter and antimatter, but the universe, since its creation, is all matter, no antimatter inside. So what happened? Is it due to the roles of the standard model or new interactions? Gravity is not even in there. So if there are new particles or new interactions, so-called beyond the standard model, they could make themselves felt. Either we are lucky and they show up immediately, but so far you would have heard that's not the case, and it's unlikely to happen at the LHC. The other way is that they could make themselves felt through small, even tiny deviations in standard model observables, and that's then where the possibility for discovery lies. You may know that the planet Uranus was discovered, Neptune was discovered through very small perturbations in the orbit of Uranus. So tiny deviations can uncover whole new worlds for you. So we better make standard model predictions very precise, and experimenters also have to make their measurements very precise. So I think this slide I wanted to include because what is the purpose of precision is to measure and explore. It's not just to falsify the standard model and boring if it's standard model and only exciting if it's beyond the standard model. I really want to argue against that. From this statement from Michelangelo Mangano, so besides some special moments in history, research is not about proving a theory is right or wrong, it's about finding how things work. So that's what we're trying to do with the standard model as well. So we do not measure Higgs couplings to find deviations, we measure to know them. I think that's a good creed. One of the possible goals of a future collider might be to measure the coupling of the Higgs to the electron. Now, what that would mean is that you would know the origin of the mass of the most important particle we have. Right? That would be of matter that of how we are made. So I think that would be a fantastic goal of the FCC to find that, and not to find deviations in it, but just know that coupling. So precision for standard model and beyond the standard model, both is necessary for both. So for falsification, here the idea is to compute promising standard model observables to high precision for easier falsification by data. So here is a selection of dye boson cross-section measurements, and here is the distribution in various accurate, so the next leading order, so first and second order corrections for various observables, digamma production, C gamma production, etc. And you see this is divided by the data that some of the next to leading order results don't work, right? The next do work. So this is really, so far this is not falsification, it works, but if it would behave like this, it would be falsified. On the other hand, if you see a new signal, then you need also verification that you need to see what is the beyond the standard model influence on certain observables to high precision, just to get the feeling, what is that signature we're seeing? What particle could that be? Could that be a squark or a gluino or an extra dimensional particle, a dilaton or something like this? All of that, both of these things are necessary in the stress testing game. Sure. I'll come to that later, but you need to use whatever is solid and can help you improve your measurements. So in some cases you should use resummation, and others you don't need to because the corrections are small enough. It depends on the case. Yeah. But I'll come at the end of the talk a bit to methods with which you try to make your prediction more accurate, and resummation is a tiny bit of that. So on the experimental side, a recent very impressive measurement by CMS is the W mass measurement. Look at this result. It's a very impressive. The method was also extremely impressive, but it's 80,360.2 MeV, and this small error, very, very much below the 1% level. So this is an enormous stress test of the standard model, and the electroweak fit, that's sort of the theory, still agrees with this measurement. There was a CDF measurement from 22 and 22 that clearly does not agree. There's something went wrong there, right? I think that is, at least that's what I would conclude. So this is an example of a very important stress, and we're moving in direction of such incredible precision, and the power that they have is what we seek. Now, most of the time, because the LHC is really a proton-proton, it means a quark-gluon collider, we really need to deal with the challenge of quantum chromodynamics, the theory of quarks and gluons. Because if we want to have precision, we should manage its correction, the QCD corrections. That's what most people in our field try to deal with. So the next few slides will be a little bit on the theory of quantum chromodynamics for those who haven't seen it yet. It will be a bit on the technical side, and afterwards we go a bit again to simpler things. So the strong force, the strong nuclear force that we discussed earlier, turns out, we can say that by now, to be described by a Lagrangian that looks quite similar to the QED Lagrangian, except instead of numbers or phases, things are matrices. That's roughly the situation. So you need traces because you have matrices, and here you have various flavors. These are the various quark fields. There's the masses of the quarks, and the gluon fields sit inside these so-called field strengths. Now, because things are matrices, there are some consequences, namely that the quanta of the force, the gluons, interact with each other. Unlike photons, they don't interact with each other. So this is a very peculiar theory, beautifully simple formulation, but its consequences are extremely messy, as any experimenter can tell you. This simple conclusion or inference was not easily reached. In the beginning of the 1960s, it was not well understood. There were lots of mesons and baryons were found in experiments, and here is a partial list, and the full Greek alphabet, even capitals, capital sigma, capital xi, were used in order to label them all, and then stars and other labels to distinguish yet more. Some pattern had to be found in this, otherwise it's just a stamp collection. So Gell-Mann and independently Zweig, they proposed that in fact there is a structure here, a so-called SU3 structure of flavor. So they came up with a quark model that up, down, and strange quarks, if you combine them in an appropriate way according to the rules of this group SU3, actually can explain these particles as combinations of those quarks. So that explained the pattern, but the force was still very strong. For example, if you think you should phrase the theory in terms of these particles as its degrees of freedom, you have a problem because the pion-nucleon coupling, for example, is about 13, not a small coupling. Right? So that was not the way to go. So the theory is phrased in terms of quarks and gluons, unobserved particles, but degrees of freedom that are there, that you can calculate with, and that you can see indirectly. So they should at least be bound strongly inside these mesons and baryons that were found. That was the theory. On the other hand, and that's the idea, to make this work, quark had to come not just as an up quark, but even in 3 different colors, 3 different varieties. Not real colors, but something we called colors. The words flavor and color all came from the 1960s. Not sure how those inspiration was reached, but one has a suspicion. And the theory then supposed to be invariant under this color space. It's a bit of a weird idea, right? That you first introduce a new quantum number and then demand that things don't matter, don't depend on this quantum number. Seemed like you're doing nothing, but this strange combination actually was very important. So the statement was quarks have 3 possible colors and pions, protons are singlets of this symmetry, and then you can start making sense of the patterns that you see. Since color is such an important quantum number, a bit of one slide on evidence for it. I gave a lecture yesterday where I said I would address this, and here is the idea. Here's a very nice, actually, evidence for colors. Even though we don't see the quantum number, we cannot see loose quarks and gluons that have the color. All we see are color neutral particles. How can you see this color? This way. Imagine you do E plus E minus collisions into a photon that then decay either to a quark-anti-quark pair or in this diagram to a mu and a mu minus and a mu plus. And you measure the cross sections for those processes and you take the ratio. So the numerator is the cross section for E plus E minus to hadrons, and downstairs E plus E minus to mu plus E minus. They're very similar cross sections, except the nature of the final state particles is different. Now, notice that if these quarks come or don't come in 3 colors, that will influence the numerator. If they come in colors, you get an extra factor of 3, and if not, you don't. Downstairs, you don't have that problem. So if you compute this at leading order, you simply get a series. These are the sum of the quark charges, 2/3, 1/3, 1/3. And if you wouldn't have this factor 3 of colors, you would get a 1.1, whereas the experimental answer is 3.6. So only if you have the 3 of color in here, then you start getting agreement. This is really indirect, but very clear evidence of color. And you see it also here in the experimental data. These are lots of data points. It's a bit scattery, but you sort of see it becoming asymptotic to 3.6 here. So beautiful and very famous variable, the R ratio. So that's a very indirect way, but even more direct evidence for the existence of quarks came in so-called deep inelastic scattering. And the nice thing is this also led to an interesting paradox, and I'll get to that. So here's a picture of deep inelastic scattering. Unfortunately, this picture time goes from right to left, so you get an electron coming in from the right, exchanging a photon and flying off at an angle. And the exchange photon hits, presumably, a quark inside the proton that comes also in from the right. Now, out of this scattering, you can define a variable called x, Bjerkane x, that you can compute from measured quantities. And it turns out that the data for such a reaction almost don't depend on this x, almost flat as a function of x, only by now very mild dependence. And to explain this, I will not do the explanation, but it turns out you could explain this if these quarks in here are very weakly bound, almost like free particles. Then you can beautifully explain that. The type of these are called partons, not baryons. Also a nice name, but it's not the right name. So now we have a paradox. Okay, quarks just tightly bound in these mesons and hadrons, and here quarks being hit and almost behaving like free particles. How can both be true? So that's the paradox. Now, a solution of the paradox would be that if the coupling behaved like this, that at high energy it's small and at low energy it's very strong. At low energy, quarks bound into hadrons, so you have a strong coupling. And at high energy, in this deep inelastic scattering experiment, you have a very weak coupling such that they almost behave like free particles. That would be nice, but if the theory that you seek does not behave like that, it is useless. So how does a coupling be that becomes energy dependent in the first place? And if it does it behave like this? And to do this, we need to briefly consider a technical topic called renormalization. If you don't care about this, don't worry. Then a few slides on, we turn to other things. But for those interested, maybe you pick up a few notions here. So to see this behavior of this coupling, we need to look at quantum effects. And quantum effects at the Feynman diagram level means loop diagrams like this, one loop diagrams. If you do such one loop diagrams, it means you have to compute integral over a loop momentum. Here is such an integral. These are not easy to do. In fact, they behave a bit like the four-dimensional integral over L to the fourth squared. That's like a logarithmic integral, and that goes up to infinity, so that's infinite. That's pretty bad. So you have a correction to a basic vertex that suddenly is infinite. That's not a good perturbation theory. That's pretty awful, the worst you can have. But it turns out you can cure this infinity by so-called renormalization procedure. And you do that by expressing the divergence temporarily in a parameter that measures the deviation from 4 dimensions, epsilon. So the divergence looks like 1 over epsilon. And if you go back to 4 dimensions, epsilon goes to 0 when you have your divergence back. But by now you can calculate with it. So the way to do that is by renormalizing your parameters, and renormalization brings in new factors of 1 over epsilon that cancel the problematic 1 over epsilon that you just had. That's the idea. And after that renormalization, your divergences are gone and you're fine. As a byproduct of this renormalization, I will not go into the formulas, you get a differential equation for your now finite coupling constant. And the differential equation looks like this. So you take a variation with respect to an energy parameter, and the whole thing is proportional to the alpha s squared and some coefficient in front with this minus sign. That minus sign is important. In fact, it's so important, a Nobel Prize was given for it in 2004 to Gross, Wilczek, and Policy, because what it says is that as you slightly increase mu, alpha s decreases because of the minus sign. So if you increase the energy, the coupling decreases. That's precisely what we were after. And QCD is the only theory that does such a thing. All other theories have a plus sign here. So it's a beautiful resolution of the paradox. So the coupling constant behaves like 1 over the logarithm of the energy. You increase the energy, the coupling goes down. That was a heavy bit, okay, but it solves the problem because now indeed alpha S does behave like this and it agrees with the data. It really shows that we understand how the strong coupling behaves. We've understood it. So this theory QCD, which we need to master in order to make precise predictions, we have now mastered. We understand its quantum behavior. It solves the paradox. We're ready for doing precise calculations with it. That with which we can stress test the standard model and using also the LHC data. Okay, so far, you with me? Okay. Are you interested, I can skip this also, interested in a bit of structure of the QCD Lagrangian? 2 slides on it? Okay, some polite nodding. So here is the, I'll do it very quickly. To build the theory, you do a bit like quantum electrodynamics. Instead of phases, you use these SU3 matrices. So you have quarks in 3 colors that you transform according to a 3 by 3 unitary matrix. This is the group of color transformations. And in order to make it invariant theory, you introduce a so-called covariant derivative with gluon fields inside in order to make it all transform nicely. And in the end, you get here the QCD Lagrangian, which I already showed you. And what you do with such a Lagrangian, this is a slightly more precise version of this, you write Feynman rules, and these are the Feynman rules for a flying quark, a flying gluon, a gluon-quark interaction, and uniquely, an interaction of a gluon, of 3 gluons. This doesn't exist in QED. In QED you have similar things for these 3, but you don't have this. This vertex, by the way, seems very esoteric, but is the reason we're all here. That minus sign that I talked about, that comes essentially due to the fact that we have this vertex. That minus sign makes sure that we have protons, that we have neutrons, that we have pions, that we exist. So you can really make a direct connection of a stupid Feynman rule and the existence of us, and of all matter around us. So this is none of these things are all that esoteric. So with these Feynman rules, we can draw Feynman diagrams and start calculating. So these are the tools, the rules with which we can do the stress testing on the theory side. Okay, now let's come back a bit to the theoretical predictions as such. So we would like to, as theorists, to think of a theoretical LHC. So we'd like to make the theory predictions the way that the LHC does. So this is the appropriate cartoon. We have 2 hadrons coming in, think 2 protons. This is the proton 1, the other proton, and they exchange, and the quark and 1 proton and the anti-quark and the other proton together collide and make some interesting final state. And the remnants fly on. This is really a picture of what happens in real life, according to similar to the movie we showed in the beginning. And this picture can be translated into a formula. Where here we have these parton distribution functions, which tells you how probable it is that you have particle J, parton J coming out of the proton. And here this as well. And this bit is what we can do with Feynman diagrams, and that corresponds to this last factor. These Fs we have to download from the web. There are groups who make these, and I won't go into how this is done. It's extremely important that this is done. But for our purposes, we consider them as downloadable from the web. They have their own uncertainties, but there's really very sophisticated and important techniques behind making the best possible parton distribution functions, so-called PDFs, not to be confused with the other kind of PDF. So with this formula, we make predictions. We calculate this as best as we can. We download the best possible sets from this. We do this integral, and we have a prediction. That's how it works. And then we compare to the data that we get from the experiments. So the whole enterprise is You have inputs, masses of particles, the Parton distribution, from coupling constants, mixing angles, lots of stuff goes in between, diagrams, calculations, Monte Carlo, it's resummation, etc. Outcomes, cross-sections, distribution, things to compute with experiment. And in order to optimize all this, you have to optimize the output, you have to optimize the input and the box in here. All these things have to be made as good as you can. So that's the theory enterprise. What about on the experimental side? Well, we are fortunate in that there's a lot of LHC data still to come. The LHC has been running for some time, well before 2021. This is the most recent schedule. Josh and I will recognize it. You see here various color codes of when protons, so these color, I won't even dare to name it. Is it green or yellow? Is it greenish? That's when the protons are colliding. There's a few runs where ions are colliding. That's good for the ALICE experiment and the others as well. And then the blue one here is hardware commissioning. You see here, next year there will be a lot of running. There's always some shutdown around Christmas because of the energy prices in Geneva. It's just unaffordable to run the LHC and also give people some holiday. And then from 26 onward, the middle of 26 onwards, almost until the first half of 2030, there will be an upgrade of the whole collider, and this is the period called Long Shutdown 3. There's been 2 before. And here the regular LHC will be upgraded to the high luminosity LHC, the HL LHC, in order to prepare to have much more intense beams colliding, and therefore much more data production, much more data gathering. Way further beyond, there's another long shutdown to go to run 4 to run 5, and so that's the projected future until about the 2040s, at which point we hope to have start preparations for a new collider. But until now, about 350 inverse femtobarn out of a total at the end of 3,000 has been gathered. So only about 10% is already on file. So we're going to get a lot more data, a lot more precise measurements. So theory has to keep up. So here's stress testing the standard model in a nutshell. It's you see here on the x-axis is a bit of an odd plot. Lots of there's no progressing variable. It's just a list of photon production, W production, TT bar production, gamma production. Lots of measured processes, and you see here the data and also the theory. And so far, what this plot shows, if you stare at it a bit longer, is it works really, really well. There is no obvious deviation. Note, however, there's also a logarithmic scale. You wouldn't see much here, right? But it shows you how well it works at the moment. It is very hard to falsify. So a lot of impressive agreement for many, many observables. I want to take a slight deviation away from the LHC for the moment because it's a nice story. Unfortunately, a story without a clear conclusion. But I want to talk a bit about about another particle, the muon, the heavy cousin of the electron, and its magnetic moment. In fact, the quantum corrections to a magnetic moment, it's anomalous magnetic moment. Now, you compute this magnetic moment, you compute it very, very precisely by computing very high order, high loop diagrams. And here are some representative diagrams. I mean, there are hundreds and hundreds, even thousands of diagrams. But here's a few. Here's the lowest order one, and this is the standard magnetic moment 2. What you're looking at is for deviations from 2. And this is called the anomalous magnetic moment of mu. And this is not a vector, a mu, this is the anomalous magnetic moment of the muon. So often this is also called G minus 2 for obvious reasons. So there's a few typical types of diagrams that have names. So this one here, where the photon goes from one leg to the other. In the meantime, it can do lots of stuff. It can briefly form a pi plus pi minus pair or a k plus pi minus. This is called the hadronic vacuum polarization contribution. And there's also a process where you have a photon here and 3 more photons here, and stuff can happen here. This is called the light by light scattering bit. And that's all understandable. If there's new physics, there might be new particles that we don't know that are still contributing to the result. Possible unknown particles. And if you are precise enough in your measurement and precise enough in your calculation, you may see evidence for the presence of this in your data that you didn't include in your theory. So it's a very difficult calculation, very difficult measurement, many people involved, lots of subtleties. And part of the interesting story is this experiment was first built and done in Brookhaven on Long Island, outside New York, quite a bit outside New York. And they did that by making a circular beam of muons, which is strange because these are unstable particles. It's not easy to keep them around long enough. Of course, relativity helps in order to do the measurement. Then after some time, Fermilab said, we'll take it over. So they took the whole ring, which is, you can sort of see how big it is here, by boat and then finally by truck, all the way from the Great Lakes, then from Chicago and then down towards Fermilab, and installed it and got it running again. And now it's here arriving at Fermilab. This is the famous Wilson Hall at Fermilab in a rather ominous weather. So got it working again, did the analysis, blind analysis of course, and had a press conference on the first measurement in 2021. This is COVID time. I remember watching it, and so 5,000 other people on the webinar and many, many more on YouTube. This is really a record audience for such a precise data theory comparison. It was really quite something. And this is what was shown. The experiment at all these digits, the last two were uncertain by 22, and the theory at the time, the best agreed upon theory, was there. And there was this is the data, and there was quite a bit of a discrepancy between theory and experiment of more than 3 sigma, and it caused a lot of excitement. There's one group that was spoiling the fun a little bit, the Wuppertal lattice, Wuppertal lattice group. They did not use exactly the same method for the hadronic vacuum polarization, this bit, that's the most important bit. The other people used E plus E minus data to get this right. They used lattice calculations to compute that, and they got a result much closer to the data. So that's a bit the status at the moment, that actually there may be some difficulty with the methods, the lattice versus A plus E minus, and there's not a resolution yet. The lattice results have been confirmed by other lattice groups, considerably closer to data, but there's other questions that are there, so there's a lot of work going on with the workshops to resolve this issue. So unfortunately, no beautiful conclusion, but a tremendous exponent of data theory precise comparison. Okay. Now back to the LHC, the high luminosity LHC. What can we do there? What can we expect? And the first thing I want to do a bit is more on the outreachy level. We had some tough slides. Is to, for Higgs production, illustrate the importance of higher order corrections. Okay. So Higgs production cross-section in perturbation theory. Now the leading order prediction, if you do such a thing, and maybe you've done it in courses, is based on this one Feynman diagram, 2 gluons colliding and producing a Higgs boson. It's one diagram, very simple. And if you want to do the next correction to that, the next to leading order, you have to compute both a one-loop diagram and some extra radiation diagrams. And these are also doable. Needs a bit more work. You can do it if you are a grad student just starting out in a week or so, if you know a bit how to do it. And be careful. If you then want to go to 3 loops, that's the record now, the next to leading order, then things got rather theoretically out of hand. You need 7 million Feynman diagrams. And not just regular. Each Feynman diagram is 3 loops. That's enormously complicated. To compute each of these, you need powerful algebra, computer algebra, and advanced mathematical tools such as dimensional regularization, Hopf algebra, elliptic functions. I'll mention something. The groups that did this, based mostly in Zurich, in Switzerland, in the end, to get the result, it took them 2 months running on 25,000 computers in parallel. So theory has become really big scale stuff. This is not sitting in your office alone in a corner and working through the night and getting an answer. This is really major stuff. Now, what is this good for? Before doing that, I want to return to Josse Mazeren, a colleague of mine at NICAF, who was also in the picture with Rohini. You all use Mathematica, I guess, or Maple. He has developed over many years a computer program called Form, and it's not the user-friendly slick interface. This is built for power, and particularly for Feynman diagrams. He has paid enormous attention to efficiency, memory use, and speed, and it's really vital for collider physics calculations. All the colleagues that do this work with Form. And it's open source, you can download it, you can play with it, you can write a little script, you can run it. It's actually quite easy to use, written in C, and it's still being developed. So that's worthwhile mentioning, a little advertisement, but for some of you who might want to look this up and play with it, it's free. Now, okay, then let's look at the value of these higher order corrections. So I'll do the story a bit in reverse. I first give you the data and some units. This is what Atlas and CMS measured. This is the rate of Higgs production measured. How well does theory fare in comparison? Now, if you did the leading order calculation, you're woefully short. Right? It's really huge discrepancy between theory and experiment. The second order took some time, and look at the huge increase. Right, first of all, it gets closer. I mean, they didn't know it at the time that they got closer, but the worry at the time was, I remember it well, that if you have this and then the second correction is almost bigger than the first, or you worry about the convergence of the series. Well, will not the third correction be there? So there was a lot of effort, including resummation, all done to see, can we get some idea? And then finally it was done in 2002, and thankfully the increase was more measured, so it looked like a reasonable progression still. But in hindsight, if this is the theory answer, we still don't reproduce the Higgs production rate. We would conclude there's new physics, we don't understand Higgs production. Only after this humongous calculation with 7 million three-loop diagrams, sorry for the one, this is from 2015, it turns out to agree. So this is really the value. Now, for those of you who only want new physics, that's disappointing. But for those who want to see how it works, this is amazing that this works, right? That this really reproduces. Now, it could be that in 2000, that the fifth order ends up there. We don't know until it's done. But given the progression, also, it's unlikely, I would say. But if you feel challenged, go ahead. You need a few resources, though. So one core process besides Higgs for stress testing is Drell-Yan. That is production of an E plus E minus or mu plus B minus pair in a quark-anti-quark collision. You can measure it beautifully precisely. In fact, here are some measurements of various forms of the Drell-Yan cross-section with uncertainties of about below 1%. And the theory uncertainties so far are of the same order or above. So theory is challenged here. So these are very important process for many reasons, which I won't get into, but here is really an arena where theory and experiment meet to do the stress testing. So theory is challenged, and to show you a little bit of how the theorists pick this up, the theorists try to make a prediction with as many n's as you can, next to, or etc. That's the number of n's is the measure of accuracy. Of precision. So you see here, this is the ratio of theory to data, and the various colors indicate more and more accuracy. So this color here is the best, more n's, triple NLL and double NLO, and that has the best ratio, the smallest error. So, and that's as a general rule, once you get that precise, now all small effects that you used to neglect as being, well, too small, not so interesting, now you start have to include them. Everything that is of order 1%, even smaller, now you have to worry about, and here are some of them mentioned. So it's not just that you have to compute the things that you already did better, you have to include lots of new stuff in your calculation, and that's where all the challenges lie. So I think I wanted to show this as really an example of an arena where the stress testing can happen. Another famous one is the top quark pair production. We're already well into the precision area, and here also here are some data points, and you see the theory lies quite well. On the data points, no sign of deviation there. what I like is in this business is this plot to show you the advantage of adding precision to your calculation. So at leading order you have this uncertainty, next to leading order this, and slowly as you did better and better, more ends, you get much smaller uncertainty, which will pay off hopefully in comparison with experiment. So also for top quark pair production, we're ready now in this game. This is an important process, difficult to work with, and again. The theorists who did this, you do this in groups, you don't do this by yourself anymore. So, at the end of the colloquium, I want to come to a few snapshots of stuff that people are working on to give you a sense. None of this will be particularly clear, but hopefully you get intrigued or at least interested. So the theory community, I think, has responded well to the precision challenge in the last 20 years, the so-called NLO revolution. I'll mention it. There's now calculations and methods to go well beyond the next to leading order, and there are many new methods have been developed. It's really healthy marketplace. Lots of young people enter this field. It's really a big challenge. No doubt some of you as well, because there's so much interesting innovation happening there. Most of it math related. The next to leading order revolution is based on, I'll just sketch it, given the time. It was realized only about 15 years ago that any one loop amplitude, no matter how many external legs, can be written as a collection of boxes, triangles, self-energies, and tadpoles. So all you have to find is these coefficients. And this has now been automated through clever tricks using so-called cuts of diagrams and other methods. And so that really has led to the next to leading order revolution. Is now automated as part of computer programs. You don't have to do it yourself anymore if you don't like to. So the frontier is now with next to leading order, and even beyond that. There's lots of methods being developed for computing these amplitudes and cross sections at such high order of accuracy. You see here a bit of I think I should update this table. There's a few more entries here. 2 to 6, 2 to 7, the table has been extended. So I want to give you 3 short bits of innovation that have come into the predictions for making very precise predictions. And that will be concluding my talk today. So the first is the QCD coupling and its asymptotic freedom behavior. But you remember that curve? I showed you the 1 loop result. By now the 5 loop result is known. So that's really amazing. Thanks to form. So here's Josse Mazeren again. And so they have done the calculation. This is still impressive. 6 days in a 32-core machine you need to run with computer algebra to get this done. And roughly the beta function is the one that tells you how fast it changes as this expansion. Alpha S squared, alpha S cubed, alpha S to the 4. And what we would be worried about is, do the coefficients in front stay reasonable, or do they start growing? In fact, they all stay reasonable. Right? So if you plot this, you see here a very nice progression and not a huge deviation from the 1 loop result. In fact, the 5 loop term only gives less than 1% change. So this shows that this asymptotic freedom business is under control. We really understand it, and it behaves very nicely in perturbation theory. People are working on 6 loops. I don't know what the status is, but no doubt it will be challenging. Okay. The next thing is a bit of a cute thing. Differential equations. This is one of these mathematical innovations that people have come up with in the last 15 years that turn out to be much more powerful than originally foreseen. I just want to give you a sketch of how it works. So if you don't care, don't bother, but roughly here's the idea. Let's take an example. The 1 loop masses box integral. We have 4 propagators here, so it's a box. And they use the momenta on these lines. And this diagram corresponds to this integral. You see here an integral over k and 4 propagators. Each of which is to the first, so they all have a square, and that's what you normally get. You can compute the answer, and here it is, in terms of 1 over epsilons and s's and pi squareds. It's a very compact answer, so we don't have to worry about what is it. We can compute it, it's simple enough. But it also can be illustrated how to see how this differential equation method works. Now, what you do now is first you write down not just this diagram, but a whole family by giving every propagator an extra exponent, A1, A2, A3, A4. I do that by hand. So the original diagram is just G1111. Right? Now, the next step is to do called integration by parts identities, or as everyone calls it, IBP. IBP identities. And how do you derive those? Actually, a very simple way. Just look at your integral, stick a total derivative in there, and this is 0. Right, you integrate a total derivative. But on the other hand, you can also carry out the derivative and see what you get. Then you get a relation between these g's, where sometimes the exponent has been raised by 1 because the derivative acts on it. So you get this sort of recursion relations between these g's when these exponents differ. Right? You sort of see how that happens. Right? So what this does, you get all these recursion relations of these families of box integrals. And in fact, this leads to, you can do a few more of those tricks, to a few master integrals from which all the other ones can be derived through such recursion relations. So a lot of effort in this business is deriving master integrals, often much fewer than the actual set of integrals. Once you have the master integrals, then you can get all the others. So in this case, there are 3 master integrals, the original diagram with 4 ones, and 2 with 2 zeros, and if the exponent is 0, the propagator is not there. There's only 2 propagators. So what you can then do is now act with a differential operator, especially construct a differential operator using Mandelstam variables to get such a differential equation on this set of 3 f's, and A is then a matrix that looks like this. Now, one clever thing that Johannes Henn came up with is to change the basis and define different variables, and then the differential equation looks very elegant. Something over x, something plus 1 over x, and an epsilon in front. And this is a beautiful result, because now you can construct a solution as a power series in epsilon. That's a dimensional regularization epsilon. And with this way, if you just solve this equation, you have your beautiful answer for much more difficult thing than the one loop expansion before. So this illustrates the differential equation method for computing Feynman integrals. So it's nice. You can compute an integral by differential equations. Seems a bit contradictory, but you can do it. Once you solve the differential equations, often the solutions are sort of iterated logarithmic integrals, and those so-called special functions called multiple polylogarithms that obey also algebras. Here's a lot of math involved. But it turns out that if you really go beyond 2 loops, then a new class of functions appears, so-called elliptic integrals. And there's a lot of literature on that, mostly from the 19th century. But all of this coming back to see, is there further structure, is there sort of algebra structure among these elliptic integrals? So here there's a lot of math, I'm suppressing a lot here, that really has helped these high order calculations and organize them. So I think this is just the impression that it's not just stupid calculations, there's a lot of innovation driven a lot by math. One thing, and this one thing I'm working on, you mentioned resummation. If you look at cross sections and you just tabulate all the logarithmic terms, those are the worst terms, then you have logs that behave like this when z goes to 1 and a subclass. This type of logarithms, we have to sum to all orders, the so-called resummation, and give structure. Now the focus has shifted to this class, and this is what I'm working on, to find all order patterns there. Much harder, but we're making progress, and there's a sizable community by now trying to see if you can also find all order structure in here to improve resummed predictions for, and thereby the accuracy of the theory predictions. Which brings me finally to the end. So only 10% of LHC data are required, so we will get demands from the experimenters for very high precision, and we very much would like to deliver that, of course. The theory community is meeting that challenge, and I think with quite spectacular progress using some of the methods I just discussed in order to make that comparison. And mathematics has a surprisingly important role that I hadn't expected in these new methods and making progress. So this is the business and the game of stress testing the standard model that requires close collaboration of theory and experiment. And I want to stress again, it will lead to knowledge of the standard model, not just for searching for deviations. And that's also a goal, but we will hopefully learn more. The whole Yukawa sector of the Standard Model is largely unexplored. So we will lead to the knowledge of the Standard Model and perhaps even to new discoveries. Thank you. Yeah. It's a while back. There we are. Yeah, this one, yeah. Yeah, it's a good question. So the things you can change here is a strong coupling, but at this order there is no strong coupling. But there are parton distribution functions. So you can vary those, and that gives you the variation. The PDFs that I introduced, they all will have PDFs. The higher orders will vary both the PDFs and the strong coupling, the alpha S. So, yeah. Yeah, nothing has been shifted under the rug here. Yeah. If the uncertainty, as is usually the case, would be vast, then you can say, well, okay, we can't conclude anything. Not even the need for higher orders. But now at least you conclude, well, either we're certainly going to need higher orders if you just had finished this. Yeah, it's for the, here we are, yeah. Yeah. Well, the nice thing is with this, you don't, it's a good question, and it's a relevant question, but the nice thing is in order to have these IBP, you don't have to do that. You can stay at the level of this symbolic representation of the integral. So in order to trust and establish this relation between these various members of this family of box integrals, you can just leave it at the symbolic level. And only when you finally conclude, there's a few master integrals I need to do, then you need to start thinking, okay, now I have to calculate them and use dimensional regularization and all that. So you don't have to do it at all the intermediate stages. Yes. Every particle with spin has a magnetic moment and an anomalous magnetic moment because spin is equal to the Bohr magneton with some factor. So focus here on the mu1 because that's the one that presumably would show effects of new physics most readily. Now people have also measured the anomalous magnetic moment of the electron. And that you can do much more precisely, 12 decimal places, much more even than in mu1. The calculations have gone to that level as well. In fact, that's maybe the most accurate quantity ever computed and measured. And it agrees to 12 decimal places. So what that tells you is that perturbative quantum field theory works. Right? And this involves also 4 and 5 loop calculations. For the tau lepton, you can do the calculation, but it's impossible to do the measurement. The decay so quick, you cannot make a beam. And for quarks, it's just the only other place that people look sometimes is for protons and all stuff, but then the theory is less clear how to do the calculations. Yeah. Mm-hmm. No, but now there's a lot of collider data in there. So you're referring to the FCC HH, the Hadron version that supposedly comes afterwards. When I'm certainly not here anymore, but yeah. Well, so now we're talking about the business of how do these groups make parton distribution functions, and what data do they use for that? So clearly you want high quality data with small uncertainties. And you also want data that probe the various quarks inside and gluon inside the protons differently. You want data that probe it for large x or small x. You want a good set of data. And you also don't want to put the data that you try to predict into the fit. Otherwise, you lose predictive power. So that's what the game is. But there's lots of data sets, some from fixed target, but many increasing these collider data where we say, look, this is clear enough. We'll use this data set for PDF fitting and then leave the other data sets for actual predictions. So it's a judicious process of decision how to do that, and the groups do that. They do that very carefully. They engage in interactions. But the other thing you want to be sure that you don't pick a set of data that may have new physics in it and you put it into the PDF fits, because you'll never find the new physics then, right? You have to. And how do you know that it's not in there? So there's a lot of discussions of that type going in. It's not easy, but it's a good question, but it's no obvious that's the answer thing. You have to be just aware and judicious.